Okay, sup, I'm Derek. Today we're going to discuss our experiences at Knott's Berry Farm and how it relates to physics. So the purpose of this project was to analyze Knott's roller coasters. Our first step to achieve this was to understand the dynamics of roller coasters. Many concepts from physics are used in roller coasters. The two main rides we will be focusing on are Boomerang and Supreme Scream.
Supreme Scream is the world's tallest vertical drop tower. It is made up of three distinct parts: the ride to the top, the momentary suspension, and the downward plunge. After carrying 12 passengers up 77 meters at 3.6 meters per second, it suddenly drops the riders in 3 seconds flat, reaching speeds of over 22 meters per second. For the purpose of the lab, we assume the ride imitates freefall, although in reality its pulley system accelerates it downward faster than the acceleration of gravity. Thus, the highest g-force of 4 g's is attainable. Due to the law of conservation of energy, Supreme Scream reaches the greatest instantaneous velocity near the bottom of the ride. The car has the maximum gravitational potential energy, MGH, at the top. As it falls, the potential energy converts to kinetic energy, 1/2 mv squared, until all the energy has been transformed. At the bottom, it bounces back halfway up the tower several times before finally coming to an end.
Boomerang is 18 years old and is a sit-down steel roller coaster. It consists of one train with 7 cars, each holding up to 4 people. The ride is 108 seconds long and runs 285 meters and 38.1 meters high. One of the specialties is how it resembles an actual boomerang, going both forward and backward, as well as the addition of a clothoid loop, introducing circular motion, as well as centripetal acceleration and force. To simplify the calculations, we assumed only one car was present in the below calculations. The first major part of Boomerang are the 2 hills, one at the beginning and one at the middle of the ride. Each hill is only reached once and serves primarily to build up potential energy to supply enough kinetic energy throughout the rest of the ride, keeping in mind non-conservative forces such as friction, all in regards to the conservation of energy. Riders can approximate this level of energy by the abrupt halt at the end of the ride to stop the cart. Since Boomerang is at rest during this phase, we could find potential energy using PE equals mgh by using the position of Boomerang on the hill. Because Boomerang is at rest and moving linearly, there is no kinetic energy, linear velocity and acceleration, and centripetal force and acceleration. The coaster has static friction as it is being held, given by Fs equals coefficient of static friction multiplied by the normal force. The main difference between the first and second hill is that the second hill already has an initial velocity, and due to friction and energy lost, and the height being 3 to 5 meters shorter, yielding a slightly different quantitative calculation. At the bottom of the hill, we assume negligible friction as a coefficient of kinetic friction is not clarified to calculate the kinetic energy. According to conservation of energy, which is kinetic energy plus potential energy initial equals kinetic energy plus potential energy final, kinetic energy turns out to be about 312,228 joules. Assuming friction is 1,058.4 newtons, however, given by Fr equals coefficient of kinetic friction, using steel, which is approximately 0.12, multiplied by normal force, we can use non-conservative force equals the negative of the change in energy to calculate, yielding a slightly different result. The velocity is approximately 26.34 meters per second.
Shortly after recovering from the massive P buildup in the beginning, a cobra loop follows where there is a certain angle of elevation to help dissipate the buildup of energy. From close examinations, the angle is roughly 38 degrees and the radius is 7.5 meters. From the energy standpoint, this bank differs very little from the top of the hill to the bottom. However, in this cobra loop, centripetal force and acceleration exist, where the centripetal force is approximately 6,898 newtons and directed towards the center of the circle it travels. Acceleration and velocity are approximately 7.66 meters per second squared and 7.57 meters per second, respectively. The car's theoretical and actual velocity may differ as the value represents max velocity before it slides off the track. However, the roller coaster is designed to hold the car in place, and friction will also be present to prevent any slipping. Following the cobra loop is a clothoid loop. To simplify calculations, we assume the coaster performs a loop in a perfect circle rather than a clothoid loop. Clothoid loops are used by roller coaster engineers because circular loops require great entry speeds to complete the loop. The greater entry speeds subject passengers to greater centripetal acceleration through the lower half of the loop, therefore greater G's. If the radius is reduced at the top of the loop, the centripetal acceleration is increased sufficiently to keep the passengers and the trains from slowing too much as they move through the top of the loop. A large radius is kept through the bottom half of the loop, thereby reducing the centripetal acceleration and the g's acting on the passengers. At the bottom, acceleration can be found using v squared over r, while force can be found using mv squared over r. At the top, normal force and weight are both directed downward and contribute to the centripetal force. Boomerang is one of the more intense roller coasters found at Knott's Berry Farm. This ride can provide minutes of excitement as people can choose what to sit to experience different perspectives. As with every roller coaster, each ride has room for improvement. Newer car models that cater to a wide variety of rides could easily solve the reported uncomfortable and bumpy ride. Another improvement could be to replace the loop with the helix, as the original problem of the ride is the exhausted time spent upside down.
The Physics Day roller coaster project was effective in allowing us to see key physics concepts being applied to the real world. The main appeal of roller coasters is the sense of insecurity they allow riders to feel, caused by varying accelerations throughout rides and manipulations on the relationship between mass and gravity. For example, tapping into the law of conservation of energy, when roller coasters such as Silver Bullet and Supreme Scream reach greater heights, their potential energy increased. When the coasters went lower, their gravitational potential energy was converted into kinetic energy, therefore speeding up the ride. Through the concepts of uniform circular motion, corkscrews, inversions, and clothoid loops on rides such as Boomerang also induce feelings of weightlessness and heaviness. Centripetal acceleration caused by rotating objects affect the normal force that seats act on the passengers, giving them sensations that deviate from the normal everyday gravitational force people experience. The Physics Day trip was overall awesome and enabled us to apply physics concepts to things we use and enjoy in everyday life, which in our case were roller coasters.